Can you guys still see my screen? Am I still sharing?
Yep, I can see it.
Okay.
Okay, so we can go ahead and get started. Thanks everyone for joining us for the 6th module in our 9-part CUDA training series. My name is Tom Papatheodore from the OLCF. Also on the line, we have Helen He and Kevin Gott from the NERSC LBL side of the organizing. Today we are joined by Bob Cravella, Robbie Searles, and Max Katz from NVIDIA. Today, Bob will start off by giving a presentation on CUDA managed memory, and then Robbie will follow up with an example exercise where you can try to work through some of the ideas that Bob has mentioned in the presentation. So Bob will be presenting for about the first hour, and then Robbie will take over for the second hour in our hands-on. If you have questions during the presentation, we ask that you please ask them in the Zoom chat. Since we're going to record this and you'll have it for later viewing for yourselves or other folks, we want to make sure to get a clean recording. So please ask those questions in chat, and then Bob will tackle them when he sees the opportunity. And then afterward, if you have questions at the end or during the hands-on, you're free to just unmute yourself and ask them. So, okay, with that, I'll go ahead and hand the mic off to Bob.
Okay, thanks, Tom. This is Bob Cravella with NVIDIA. I'm on the solution architecture team at NVIDIA, and I'm joined by my colleagues, Max and Robbie, who were mentioned already. They're on the solution architecture team as well. I'd like to start by thanking the folks at Oak Ridge and the folks at NERSC for providing all the assistance to make this possible. So as Tom mentioned, today we're going to be talking about something called CUDA Managed Memory. It's also called CUDA Unified Memory. So if you look in the programming guide, it'll be referred to as Unified Memory, but it's essentially a synonym to call it Managed Memory. I'd like to start with basically a caveat, and that is that, as we'll see, CUDA Unified Memory can simplify the task of programming GPUs, of getting your work done on a GPU. However, I'd like to caution everyone that unified memory is not necessarily a technique to achieve higher performance with your code. Many new developers will approach this subject thinking CUDA Unified Memory or Managed Memory is a way to make my code run faster. That's generally not what the purpose of it is, and I think by the end of this presentation, you'll have a good idea of that. So what is CUDA Unified Memory all about? We're going to talk about that in just a moment. We will cover the basics of managed memory. We will talk about some specific features of it, like demand paging, oversubscription, and some other features. We will talk about some use cases, typical ways that people might use managed memory to perhaps simplify a programming task. And we will pretty much finish our discussion talking about performance. This will be an extended discussion of performance, talking about the basic performance of unified memory, as well as some API-level techniques and methods that are provided within CUDA to allow you to sort of optimize the performance of unified memory. And as we finish, we will, as usual, have suggestions for further study and the homework. And towards the end of this presentation, as Tom mentioned, when we get to the end of the prepared material, I will pause and make sure that I have caught up on any questions that are in the chat, and we'll also open the mic up at that point for spoken questions. And once we see that the questions have died down, then I will turn it over to Robbie Searles, and Robbie will have some exercises to walk through from the homework. So I will also be stopping at points, or at least maybe one point during the presentation, to catch up on questions that may be in the chat at that point. So what is the idea behind unified memory? I'd like to start with a motivation, an idea that we're trying to achieve. And so you may remember from our very first session that essentially any program that uses the GPU for computational tasks has a three-step sequence embedded somewhere in it. The first step is to copy the data to the GPU. The second step is to run your program, your CUDA kernel on the GPU to process that data. And the third step is to copy the results back from the GPU to the CPU. This is pretty much true no matter how you're using a GPU if you're using it for computation tasks. That's always going to be present. As a CUDA programmer, you know that this three-step sequence is something that's visible, that's evident in source code. You're going to write source code that is going to perform the tasks necessary for step 1, source code for task 2, and source code for task 3. However, task 1 and task 3, as depicted on this slide, are not things that you might typically see embedded in an ordinary C or C++ program, if that program is designed to run on the CPU, on the host. And so these become extras that you have to learn about and deploy as a CUDA programmer. It's boilerplate, if I can use that word, that you have to add to your CUDA program to make the GPU a usable processor. And so wouldn't it be nice if we had a way to essentially eliminate or try to eliminate the boilerplate associated with steps 1 and 3? Wouldn't it be nice if we just simply didn't have to write code for steps 1 and 3? When we have our data ready, we just launch our kernel and we're off. That is the motivating and fundamental idea behind unified memory or managed memory. And as we see, unified memory and managed memory we will see, is not something that was present in the CUDA programming model from day one. Now, we've run into this idea before. The CUDA programming model evolves over time, and in our last session, we saw that, for example, warp shuffle was a methodology that was not present in the CUDA programming model from day one. It was something that was added, roughly speaking, in the 2012 timeframe with the introduction of Kepler GPUs. Unified memory is also one of those things that was not present in the original CUDA design and was added to the CUDA programming model, actually in about the same time frame. So in that time frame, in roughly the 2012 or 2013 time frame, approximately in the era of CUDA 6, approximately in the era when Kepler GPUs were first introduced, the unified memory model was introduced to the programmer. It was available, the API was developed to support it. And that model had some goals which are depicted on the right-hand side of the slide. First of all, we want to simplify the programming model and, in particular, simplify the memory model. As you know from our previous sessions, the CUDA programmer, based on what we've learned so far, needs to essentially create two copies of each data that's going to be used on the GPU. You'll have a copy on the host and a copy on the device, at least with respect to steps 1 and 3. For any input data that flows to the device and any output data that comes from the device back to the host, you've essentially got two parallel copies of that data, one existing in host memory, one existing in device memory, and there is API calls to manage all that, additional allocation calls and copying calls. So unified memory simplifies all that by the simplifying idea is that instead of having to have these two parallel pointers, let's refer to one as the host pointer and the other as the device pointer, but essentially referring to the same data, now we're just going to have one pointer. And somehow that one pointer is going to be usable whether I'm using it in host code or whether I'm using it in device code. And as a result of that simplification, I now essentially, from the programmer's perspective, have only one copy of the data to think about and to manage. And so because we only have one pointer, there's no copying needed. This also, as we'll see, can simplify code porting. I'm going to come back to that once or twice. So for now, let's just latch onto that idea that this may simplify the process of code porting. As we'll see, the mechanism to make this single pointer magic work involves the 1, 2, 3 sequence. However, now steps 1 and steps 3 of this sequence are somehow being managed by what I'm going to call the CUDA runtime. Let's just refer to that or think about that as the operating system that makes the GPU usable in the CUDA programming environment. And so the CUDA runtime is this executive or entity that is, based on the source code that you write, is performing steps 1 and steps 3. There's no magic here. We haven't changed the fact that the GPU is an appendage to the machine. We haven't changed the fact that this is a heterogeneous computing environment. We haven't changed the fact that fundamentally and ultimately steps 1 and 3 are still needed. But what we have done is simplified the programming aspect from the programmer's viewpoint. And so this means that the operating system, in other words, the CUDA runtime, is going to pay attention to the code you write, and at runtime, it's going to affect movement of the data for you on your behalf. And as a result of that movement of the data, which we're going to refer to as migrating the data, the objective then is the runtime will migrate the data to the processor that needs it. This mechanism of migrating data and having it essentially present for only one processor at a time helps to allow for what we call global coherence. Because there's only one copy of the data in existence at any given time, and it's got a location associated with a particular processor, the processor that's acting on it, we don't have race conditions that result from two processors acting on the same memory location at the same time. It doesn't mean that all race conditions or concerns about sequencing disappear with this. We still have two processors that in a sense are accessing the same data, but they are not given access to the data at precisely the same instant, at precisely the same clock cycle. And as a result of this, this becomes a mechanism by which we can help to attain global coherence using this methodology. And as we'll see, this technique, this unified memory technique, can still allow for, it interoperates with the rest of the CUDA API, and itself can still allow for explicit hand tuning. We'll get to that towards the end of this presentation. Now, as I mentioned, this initial unified memory model was introduced in CUDA 6, approximately the 2012 or 2013 timeframe, roughly coincident with the introduction of Kepler GPUs. Probably for the purposes of this audience, mostly focused on modern HPC machines like Summit and Cori, those machines are using a much newer processor. They're using Volta processors. And so as time went on, some extensions or additions or improvements in the capability and functionality of unified memory were made. And those improvements were made primarily around the CUDA 8 timeframe. So with CUDA 8 and beyond, and in particular when our processor is of the Pascal generation and beyond, which applies for machines like Summit and Cori. Volta is the generation after Pascal. For those types of environments, CUDA 8 and beyond, and if my processor is a Pascal processor and beyond, we introduce some new capabilities into unified memory. In particular, one of the most important new capabilities that we're introducing is something called demand paging. And demand paging is going to underpin some of these other pieces of new functionality that I'm going to talk about. So the first piece of new functionality I'm going to talk about is an idea called oversubscription of GPU memory. If you're a CUDA programmer, and let's say you're working on Summit, and that has typically Tesla V100 16 gigabyte GPUs, and so that means the CUDA programmer has up to 16 gigabytes, or a little bit less than that, but approximately 16 gigabytes of memory, of GPU memory, that they can allocate using CUDA malloc. Anything beyond that with a CUDA malloc call, any attempt to reserve more than that amount of memory would result in an out-of-memory error being returned by the CUDA malloc call. And that's all you have to work with based on the methodology of CUDA that we've been using up until now. However, with unified memory and with the new allocator that we're about to introduce, you can oversubscribe GPU memory. We're going to come back to this topic, so I don't want to completely unpack it just yet. But the idea is the 16 gigabyte limitation is no longer necessarily a limitation. And somehow the unified memory subsystem will allow you to pretend as if your GPU has more than 16 gigabytes of memory and somehow make that work for you. Okay? Now we're typically going to run into a next limit with our managed allocation strategy that's associated with system memory size instead of GPU memory size. It won't be the whole system memory size, but it will be something approximating the system memory size as our upper bound for managed allocations. We continue to provide for GPU, CPU data coherence. You're going to see an example of how this works using demand paging. And in addition, we've now provided for a new capability, and that is for what we call unified memory atomic operations. And in a nutshell, what this means is that multiple processors will be able to do atomic operations on managed allocations, even if those allocations are currently resident somewhere else and have all of the expected atomic capabilities apply. So the atomics will work as expected to sort out inter-processor communication or inter-processor simultaneous access. Those atomics will work out even when they are being performed on separate processors in the system. For example, atomics from the host on the CPU and atomics from the device on the GPU accessing the same atomic location or the same location. And we are going to continue to extend your capability to tune unified memory performance. Again, I want to reserve that topic because we're going to drill into it in more detail later in the presentation. So these are some of the new features that were introduced with the CUDA 8 evolution and are currently in effect for unified memory. This will be our focus for most of the discussion. I'll briefly touch on what are the characteristics of what I'm going to call the pre-Pascal regime. That's the one we looked at on the previous slide. I'll have one more slide to talk about that, but we're mostly going to put those topics aside, and we're going to focus for the rest of this presentation primarily on this behavior, which, as I mentioned, is underpinned by this ability that we're calling demand paging. And we'll get a better idea of what that means exactly in just a moment. So let's take a look at what this means for writing your code. We have what's depicted on this slide is something, a function that is primarily designed to sort some data. So it's assume that data exists in your file system, and on the left-hand side, we see some CPU code that if I called this function, we can observe the behavior. Basically, we're going to create an allocation, and we're going to read that data from the file system into the allocation. Then we're going to call a function. We're calling it qsort, so let's just pretend that's some kind of sorting function. And then we may have some other operations that we need to do, and we'll just refer to that using the useData function call. So this is not necessarily that interesting piece of code, but it identifies a typical sequence where we have to access or retrieve some data, and then we're going to operate on that data, and then we're going to use that data in some other fashion. If we were going to port this to run on the GPU using CUDA, we might say, well, of course, I'm not that interested in reading from the file system. That's not what GPU acceleration is all about, primarily, at least for this purpose of this discussion. And maybe the useData stuff is relatively trivial, so I don't need to port that. But the sorting function, that might be something that I want to port and run on the GPU, because maybe the GPU can do that more quickly than the CPU can. And so if that were my focus for porting, I might end up with the code that's depicted on the right, using the methodologies that we have learned up until now. So I have my data. I'm going to create an allocation for that data in host memory now using malloc. I'm then going to create, let me just call it a parallel allocation in device memory using CUDA malloc. This is very typical, and this is part of our step 1 processing sequence. Then I'm going to read the data from the file system into host memory. That's through using the data pointer on the fread call. And then I have to transfer that data to the GPU, so I'm going to write my CUDA memcopy operation to transfer from my host pointer data to my device pointer, d_data. And at this point, I have completed step 1 of my CUDA processing sequence. And then I'm going to go to step 2, which is to run my kernel, and somehow this kernel is going to sort the data. And that completes step 2 of the processing sequence. And then for step 3, I copy the results back to my host pointer. That's step 3 of the processing sequence. And then the remainder of the code is roughly the same as what I would see for ordinary host processing of the data. So let's make a couple observations. First of all, we see the evidence of the 1, 2, 3 processing sequence on the right-hand side. And we see that this has created some bloat in our code. We have to use additional lines of source code in order to create this CUDA realization. And one argument could be made that the more lines of source code you have, the more complicated your code is, and the more chances you have for the possibility of introduced bugs. And so code bloat and this sort of boilerplate is not something that we as programmers particularly enjoy or relish. It's up until now, it's been a necessary fact of life using the CUDA programming model that we've depicted here. what would this look like if we were going to use unified memory? If we were going to use unified memory, it would look something like this. We see, first of all, we'll go through the code in a moment, but we see, first of all, that there now appears to be approximately the same number of lines of code on the right-hand side as are on the left-hand side. In fact, it's one extra line. We also see that our steps 1 and steps 3 are not as obvious, and those have been sort of subsumed by the managed memory subsystem. And we also observe that there's approximately a 1-to-1 correspondence between the lines of code that we write on the left-hand side and the lines of code that we write on the right-hand side. So let's go through that and see what are the differences. First of all, we're now saying to use unified memory, what you will do is replace your ordinary system allocator. In this case, it's malloc, but it could be new or perhaps some other allocator. You will replace your ordinary system allocator calls with one from the CUDA runtime API. In particular, it's called CUDA malloc managed. And like every other CUDA runtime API call, it returns an error code. So we haven't depicted the handling of that return, but as a good CUDA programmer, you've already learned that you want to pay attention to those error codes. But the line of code would be CUDA malloc managed, and it would look a lot like a CUDA malloc call. It takes a pointer that is going to be adjusted to be the pointer pointing to the allocation, and it takes a size in bytes, just like CUDA malloc does. So we're replacing our usage of a system allocator, a host memory allocator, with a so-called managed allocator, in particular, in this case, CUDA malloc managed. And we see no evidence of CUDA malloc itself anywhere in this code. Then we can continue with our ordinary host code using that allocation, that pointer that I just allocated with the managed allocator. Using that data pointer, only one pointer now to refer to this data. Using that same data pointer, I can read from my file system into that allocation. Then, using the same pointer, data, I can call my kernel call. There's no CUDA memcopy required at this point. I can just call the kernel, and somehow this data pointer can be used in device code in a fashion similar to the way the pointer that was returned by CUDA malloc can be used. It's providing an allocation that's usable in device code. Our one extra line of code here is a synchronized call. One of the things we can't get away from is the fact that we still have a two-processor system. We still have the CPU processor and the GPU processor, and the GPU processor at the point of the kernel call runs asynchronously. That means it's kind of like fire and forget. The call launches at the point of my kernel launch, but we don't know exactly when that kernel will end, and the CPU code would continue on. The CPU host thread would continue on with the next statement after the kernel launch, even before the kernel has finished executing. Now, in that scenario, if our next piece of code called useData here intends to work on that data that I'm currently sorting, then we want to make sure that that useData function call doesn't begin until the data sorting is complete. Since the data sorting is happening on the device, we already know of a CUDA runtime API call that we can use to enforce that synchronization. That's called CUDA device synchronize. So the CPU thread stops at the CUDA device synchronize call until the kernel is complete. If we had the previous realization in using CUDA memcopy, the same thing would have happened because CUDA memcopy is a blocking call. It waits for all previous CUDA activity to complete before the host thread, before the copy operation will begin, and before the host thread is allowed to continue. So the host thread would have stopped here after the kernel anyway in our previous realization. But now we don't need to do any explicit copying, so all we need is the blocking behavior, and CUDA device synchronize gives us that in a packaged call. Once the CPU thread proceeds beyond the CUDA device synchronize, we know that the data is coherent, it's already been sorted, it's ready, and useData can then proceed to operate however it operates on the sorted data. And when we're done, since we have allocated data with a managed allocator, we don't use ordinary free on it, instead we use CUDA free. But that basically summarizes the entire code porting process using a managed allocator. We've touched on all the major points that you need to be aware of when you're using unified memory. And this will give you functional code using unified memory with the benefit of reduced lines of source code, if nothing else. Let's point out then some of the most important features. With on-demand paging, the unified memory allocation is creating an allocation actually that is usable both on the host and the device. Okay, so that data pointer, which we have allocated using CUDA-malloc manage, can be used equivalently in host code or device code. And so if I wanted to immediately follow my CUDA-malloc manage call with, let's say, a memset to initialize that memory to 0, because CUDA-malloc doesn't initialize memory, just like CUDA-malloc doesn't initialize memory, just like malloc doesn't initialize memory. If I wanted to initialize that memory, which would be probably pretty typical if it's input data, then I might use a memset call. This is a call that's an ordinary host code call, and that call will be able to access all of the data that's referred to by the allocation, by the data pointer. That will be able to access it all as if it were allocated using malloc or some other ordinary host allocator. I can then immediately access all of my values in the kernel. Now, this example is something that we're going to unpack on our next slide. We're going to look in detail at the paging, the demand paging process, and what does that mean? What happens at the point of allocation? What happens when I touch the code? And so forth. We're going to go through that in some detail. So let's understand what this code is doing. When I get to the point of the kernel call, when I run the memset call, I've simply initialized all my data, the entire allocation, to 0. But when I get to the point of my kernel call for set value, what you can see is this is only setting a particular location. If you look at that CUDA kernel that's depicted on the top of the slide called set value, it's taking an index location, and the only thing it's doing, one or however many threads you launch, they're all doing the same thing. The only thing it's doing is taking that index location, or that location referenced by index, and setting it equal to the value that you processed or that you pass. So if I call set value as I'm depicting down below using the data pointer, it's going to go to the location at size over 2 in that allocation, and it's going to set that location to 5. That's it. So this kernel is only touching basically one location out of this entire allocation. And then I use a CUDA device synchronize call to make sure that I have given the kernel the opportunity to run, and then I can use data. And I can expect at that point of use data that my location indicated by the index value has been properly set. All right, I see that there are questions in the comments, and I'm going to come back to those in about 1 or 2 slides, so just bear with me. What I'd like to do now is demonstrate some of the underlying behavior when we execute this code, okay? So the first thing that we observe is that I have a representation here of CPU memory on the right-hand side, and I'm going to depict some lines of CPU code above that. And I have a representation of GPU memory on the left-hand side, and I'm going to depict in a moment some lines of code that would be affecting the GPU side. And of course, we know that there is a physical interconnect on a system like Summit that is NVLink, but on other systems it could be PCI Express. There's a physical interconnect that is somehow allowing for the transfer of data, the migration of data as needed. And we're going to see how that works in detail. So the first thing that's going to happen is that I'm going to hit the CUDA-malloc manage call. This, of course, is running in the CPU code. And we will assume that for the time being, for the moment, we have effectively carved out an allocation. We've told the CPU host operating system that there is now a memory area reserved. Okay? This is getting into the details of the stepwise sequence that happens when you actually run a call like malloc. I'm going to try and not get too far into the details, but there are some important points that I want to make. And the first important point that I want to make is we have reserved space with this CUDA-malloc manage call, but we have not necessarily brought any pages into existence yet. And I will cover what that means in just a moment. So this initial allocation is effectively reserving space, but it is not necessarily bringing that allocation into existence. The next line of code that we're going to hit is our memset. And what we know about the memset is that it's going to go through the allocation and it's going to set every location to 0. Okay? So let me run that sequence again. This is our CUDA-malloc managed. We've identified, marked out the space for our allocation, but haven't actually initialized or touched any of the data yet. And then when I run the memset call, we get what are a sequence of page faults. A page is a subdivision of memory, and any allocation therefore consists of one or several pages. And so we can imagine any number of pages. And as I begin to touch that memory to access it using memset, every time I access something that has been reserved but not brought into existence, a page fault is created. And the page fault causes the operating system to actually instantiate that page and make it physically accessible. And then it returns control to the memset routine, which populates that page with zeros in this case. That's not a valid memset call because I haven't included what I'm setting it to, so I apologize for that. That's an error in the slide that I just noted now. But nevertheless, you could imagine that memset call having a 0 parameter in the middle, and that would initialize all of this allocation to 0. And it's going to do that by moving through the allocation sequentially, and as it crosses a page boundary every time, it's going to trigger a new page fault. That will be a host operating system interaction, which will bring the memory, physical memory, into existence and allow it to be mapped and accessed, and the memset call will proceed. At this point, our data is all present and properly instantiated in host memory. Okay? Now, our next call in CPU code is to run our set value, which is a kernel launch. So this launches a kernel, in other words, device code to operate on the GPU side. And our kernel on the GPU side, as we've already seen, has just a single line in it, and as we know, that single line is essentially just going to touch one location in GPU memory, and it's going to set that single location. So what happens when I actually execute that code? Well, I trigger another page fault. This time the page fault is on the GPU. And the effect of that page fault is to cause the data to move from the CPU to GPU. This is important because I need to acknowledge or provide for the fact that this data was initialized. I can't just instantiate it or bring it into existence. I have to actually migrate it or move it or copy it from host memory to device memory, and that copying action is triggered by the page fault. In this case, the page fault is on the GPU, and in this case, it triggers a copying of data from the host to the device. Once the page faulting operation is complete, then the GPU code is allowed to proceed with whatever it was going to do. And in this case, whatever it was going to do is to set that value in that location to the value indicated in the kernel call, which was 5 in this case. So that essentially constitutes everything that you probably need to know about the behavior of managed memory. It points out the fact that an allocation brought into existence doesn't necessarily have a physical mapping yet. The page faults trigger the physical mapping, and the page faults can happen on the CPU or the GPU, and if the data is already mapped somewhere else, the page fault will trigger a migration. So we could imagine this process happening in reverse. We could imagine doing a CUDA-malloc managed, and then launching a CUDA kernel to initialize the data instead of memset, in which case all of my page faults would have happened on the left-hand side. And then at the completion of that CUDA kernel, I could imagine some CPU code that's just touching one location, and touching one location would trigger one page fault on the CPU side, and that would trigger a migration of data from left to right, from GPU to CPU. So the same concepts apply whether I am working in the host or the device. Okay, let me pause now and see if I can answer some questions that are in the chat. So the first question that I see is, what is the difference between pinned memory, unified, managed? Well, at the beginning of this discussion, I talked about the idea that unified memory and managed memory are synonyms of each other. Okay? You can see where the managed memory word comes from because the word managed is in the API. It's in the actual CUDA-malloc managed call. And so we refer to it as managed memory sometimes. If you look in the programming guide, you'll see it's referred to as unified memory. And you can think of this as a unification of CPU and GPU memory. That's where that term comes from. So unified memory and managed memory are synonyms. They mean the same thing. Pinned memory is something different. Pinned memory is memory that is always in the host. It's always CPU memory, but it is somehow accessible or mapped into the GPU address space. For more details on pinned memory, I'm going to ask you to wait until we get to our next session on concurrency. So that'll be next month. We will talk about pinned memory. I'll explain what it is in more detail and why it's important in the CUDA programming model. But for the moment, we really haven't talked about pinned memory, and so I'm giving you just that brief definition. When we get to next month, there will be a better, a more in-depth explanation. The next question is, if I use CUDA malloc manage to allocate memory, but never use the memory on the device, does it have a cost compared to regular malloc? I expect that it does. I assume the word cost here means a performance cost. And one of the costs that we could expect is that there is a demand paging process that is going to come into play, or demand paging isn't the right word, perhaps, but it's a on-demand creation using something like demand paging to creation or instantiation or bringing that memory into existence. Typically, if you use malloc, something else that is similar to that also happens. So if I use malloc, usually this is getting into system implementation details here, so this is not written in stone. It's not a function of the C programming language or anything like that. But if I look at the way malloc is implemented under the hood on a Linux operating system, you will often observe that malloc does something similar. It carves out a space in the address map, but it doesn't actually physically create physical pages of memory corresponding to that allocation until you touch that, until you actually use that allocation. That's implementation-specific behavior. I'm not suggesting that's the same as CUDA malloc manage, but I'm suggesting there's some similarities insofar as I've described it. And I wouldn't be surprised if the underlying paging system that supports CUDA malloc manage, even if it's only used in host code, might be slower on initial touch than what you would experience just using malloc. Furthermore, I don't want to go into the details now, but CPU caching behavior could be different as well. And so you may observe a higher bandwidth from CPU code to access an ordinary allocation called malloc, using, let's say, malloc, as compared to an allocation using CUDA malloc manage, even if you never touch that allocation in device code. Yes, there may be performance differences. Let's see, there's questions, continuing questions in the chat, so let me see if I can cover those. Efficiency, does each discrete set value trigger a fault, or is there some bundling that can happen? A fault occurs when the memory that I have touched is not physically instantiated on that processor. And we saw a pictorial example of that on the slide right now. The page fault occurred when that page was not present or resident on the GPU, and it resulted in the migration of data and the physical instantiation of that page in GPU memory. After that page fault occurs, any additional code touching that page has no slowdown. There's no overhead. It just proceeds at its ordinary rate. So a page fault typically only occurs once on the first code in whatever CUDA thread that may be to touch that page, and subsequent threads touching that page typically will not observe a page fault. They will just proceed at their ordinary rate. Now, if I have some kind of thrashing going on, then those statements that I just made may have to be modified. If I'm accessing the code at a high rate, both on the CPU and the GPU, this page is going to move back and forth. Okay? So that means I could have multiple page faults for the same page in GPU code if I'm simultaneously accessing it from another processor. But without that concern for simultaneous access, if I'm just doing a sequence of operations more or less what I depict here, there would be only one page fault per page. Let's see. are the CPU pages allocated with CUDA malloc manage mapped by the OS page fault handler or something in the CUDA runtime and or NVIDIA UVM driver? Sorry, I don't wish to answer that question. If we have time in the open discussion at the end and Max is willing to tackle that, I may ask Max or Robbie to try and tackle that, but I'm not wanting to drill into that right now. Also, does GPU Direct RDMA fit somewhere in the picture here? Basically, I would say no. GPU Direct RDMA is more or less orthogonal to this, and we're not really going to cover GPU Direct RDMA anywhere in this CUDA training series that I can think of. But let me just describe it very briefly. GPU Direct RDMA fundamentally establishes a buffer on the GPU that can be directly accessed over PCI Express from a third-party device like a network adapter. And that's its typical usage, actually. Okay, so GPU Direct RDMA allows data to flow from a buffer in the GPU to a third-party device or the other way across PCI Express. That buffer in the GPU is not allocated using CUDA malloc manage. It cannot be allocated using CUDA malloc manage. Instead, there's another mechanism that creates that buffer. And in fact, that buffer is mostly hidden from the view of the CUDA programmer. What the CUDA programmer observes is that I can take an allocation on the GPU, for example, a managed allocation, and I can transfer that to my network adapter across PCI Express. The details of that mechanism are not something that I want to talk about and are not directly evident to the CUDA programmer. The CUDA programmer doesn't see all the footwork that's going on underneath the hood to make that kind of direct transfer possible, and there may be buffers associated with that that are not allocated by CUDA malloc manage. In fact, they're not allocated by the programmer. Okay, but the fundamental idea is I can take an allocation using CUDA malloc or CUDA malloc manage, the pointer referencing that allocation, and I can transfer that directly to the network adapter, presumably to transfer it to another system. Okay, so let me continue. I think I've gotten to the end of the chat. Let me continue now. So I mentioned that I would come back and have one more slide to talk about what I referred to as the pre-Pascal regime. So the pre-Pascal regime would be in effect if you're using an older version of CUDA, like something before CUDA 8. It would be in effect if you are using a processor prior to the Pascal family, like Kepler or Maxwell. And it would also be in effect if you're on Windows. Okay, so this demand paging process that I've described does not apply to Windows CUDA GPUs. It applies to Linux only. And it requires a newer GPU, like a Pascal or newer GPU. And it requires a new enough CUDA version, like CUDA 8 or beyond. If you're working on a machine like Summit or Cori, those are all true statements. So you have the demand paging regime in effect, and that's why the majority of this presentation is really focused on that newer technology, newer capability. But for completeness, I want to just briefly mention a few things about the pre-Pascal regime. It looks pretty similar. In fact, all of the source code that I've shown you so far works exactly as I've shown. In other words, it's correctly written. I don't mean the underlying demand paging behavior is the same, but I mean it works correctly, just as we have written it in the slides that we have looked at so far. There are some differences in the underlying behavior. One of the differences is that managed data, stuff that you allocated with CUDA malloc manage, is moved en masse at the point of kernel launch rather than via demand paging. So at the point of kernel launch in this older regime, you could imagine that there is a hidden CUDA memcopy call for all of your managed allocations. Even data that you don't appear to be explicitly using in your kernel, like a pointer that does not appear to be showing up in your kernel arguments. A managed pointer, even if it doesn't show up in your kernel arguments, will still be migrated en masse in this system. And some of the reasons for that may become evident later. After a kernel launch, a CUDA device synchronize is necessary before CPU code touches the allocation. If you forget to do that, you will trigger a seg fault in host code. Okay? On the device, in the newer regime, you observe something different. If I omit the CUDA device synchronize call, the CPU can still touch the managed allocation. It can still work with it. In that case, I might be introducing a race condition, or perhaps as a programmer, I've found some other way to manage that concurrent access and to make it work correctly, and that might be desirable behavior. Nevertheless, you're not going to hit a seg fault. Both the CPU and the GPU can access a managed allocation at the same time. In the pre-Pascal regime, that's not true, and an attempt to do so will trigger a page fault in host code. In order to give the managed allocation visibility back to the host code, you must use a CUDA device synchronize after a kernel call. So one of the fallouts of that is that there is no capability for concurrent access as I've described. There is no on-demand migration to the GPU, and we also do not support oversubscription in this regime. Otherwise, the description of how to use it is essentially identical to what we've covered so far. All right, so that's as much as I want to say about what I'm referring to as the pre-Pascal regime. The modern regime I'm referring to as Pascal Plus. So wherever you see Pascal Plus here, I mean Pascal, Volta, Turing, Ampere, using CUDA 8 or beyond on Linux. Okay, and again, machines, modern HPC machines like Summit and Cori fall into that category. All right, so let's talk about oversubscription now. This shouldn't take long. The basic idea is that I can create an allocation using CUDA malloc managed that appears to exceed my memory size. For example, what we're depicting here is a 64 gigabyte allocation that's indicated by the size variable. And this CUDA malloc managed operation should proceed correctly on a machine like Summit. If you tried this in the pre-Pascal regime, it would trigger an out-of-memory error, okay? Or if you tried this on Kepler and Maxwell, which is the pre-Pascal regime. Obviously, not all 64 gigabytes of this data can be physically resident in GPU memory at the same time, because the GPU only has 16 gigabytes. Or even if you had a machine with a Tesla V132 gig, you'd only have 32 gigabytes. So obviously, not all of this data can be resident at the same time. But hopefully, if you apply what you've learned now about the demand paging system, you can imagine how this works. As kernel code, let's say, touches this allocation, any pages that are not physically resident will be brought into residency on the GPU memory by the demand paging system. Now, when I run up or run out of GPU memory using that process, something has to give. And what gives is that pages that were not recently touched will be evicted. They will be no longer physically resident in the GPU memory map. They're still available in the GPU memory map. They're just not physically resident. And so if code then touches an evicted page, that will cause the migration of that page back to the GPU again, okay? So there's no free lunch. You don't get 64 gigabytes of memory just as if you had 16 gigabytes in a 16 gig GPU. There is potentially some cost to be paid for this flexibility. But that cost typically shows up in the form of latency. And as we learned in our sessions 3 and 4, latency hiding is what the GPU is all about. And so it's possible to make this sort of oversubscription allocation work in an interesting way for some use cases, even though all the memory can't be physically resident on the GPU at the same time. Even all the data can't be physically resident on the GPU at the same time. Okay, so that's oversubscription, a neat feature. We've also talked about this idea of concurrent access, CPU and GPU access to the same allocation. I don't need any synchronization if I don't want to. I can launch a kernel, which is presumably accessing the data, and at the same time, my CPU code can access the data. Now, I'm using you can imagine or pretend that I'm saying at the same time here in air quotes, because what actually happens under the hood is CPU code touches the data, or let's say GPU code touches the data, and potentially a page fault is triggered. That page is brought into residence in GPU memory. The GPU code is then allowed to proceed and modify that data. Then potentially at almost the same time, or even at the same time, the CPU code wants to access that same page, And so it triggers a page fault, and the page is then moved back to the CPU so that the CPU code can access it and do whatever it wants. Now, with limited usage of this capability, you can have some very interesting use cases. You can also imagine that if I just have code willy-nilly hammering on the same page, both on the CPU and the GPU, that's probably a recipe for trouble. And what I mean by trouble here is very dismal or disappointing performance. Not to say that it won't work. You should still be able to get correct results, but it may run horribly slow, okay, because the demand paging system introduces substantial overhead. Furthermore, this doesn't necessarily somehow magically sort out ordering or coherency issues. If my GPU code touches the data, it will update that data. If my CPU code touches the same page, it will also update that page. But in the code that I've depicted here, we know that the kernel launch is asynchronous, so we have no judge for when and how the GPU code is running relative to the following CPU code. They're running at the same time, and I have really no relative basis to judge which is going to happen first. And managed memory doesn't sort that out for you. So if you have to have visibility and ordering between CPU access to a managed allocation and GPU accesses to the same managed allocation concurrently, you're going to have to sort that out as a CUDA programmer. You might use atomics to help with that, for example. Speaking of atomics, system-wide atomics are now possible. This means that any processor, for the moment, the processors that we have in view are the CPU and the GPU. We haven't talked much about a multi-GPU system, but those are certainly possible. And if you're a programmer on Summit or Cori, you know that you have multiple GPUs available to you. We're going to talk a little bit about multi-GPU programming in our next session on concurrency, so I'm getting ahead of myself a little bit here. But the system-wide atomics also apply to a multi-GPU system. So they apply to however many processors you have in your system, one CPU plus however many GPUs. And the system-wide atomics allow you to access a managed allocation from all processors atomically. Okay, so I can do that read, modify, write that we talked about in our last session. I can do it from GPU 1 and CPU 1, and both of those operations will proceed uninterrupted on that managed allocation. You'll note that the API call here looks a little bit different. Last time we had something called atomic add. This is a new version of atomic add called atomic add _ system that you have to use. But with that change, you now have system-wide atomic coherency provided for and supported by the managed memory system and the underlying demand paging. This particular feature is also dependent on the new regime. It's not available in the old regime. So let's switch gears now and talk about, okay, there's one new question in the chat, and it says, how is Jetson different even though it uses Maxwell? The topic of Jetson memory is fairly involved. There's a number of nuances. But the first thing to note in a Jetson operating system or a Jetson environment is that the host and the device memory are physically the same thing. They're the same DRAM. Okay? And so for those of you who don't know what Jetson is, Jetson refers to NVIDIA's system on a chip processor family. So these are devices, processors, if you will, that consist of typically ARM core CPUs, multiple ARM cores, plus a GPU core. And I'm using the word core there a little bit differently, so let me just say plus a GPU, plus other I/O devices and other peripherals, all integrated onto the same chip. We call that a system on a chip methodology or design, and Jetson is a family of products that are all SoC or system on a chip designs. They all consist of varying configurations of ARM cores and a GPU. The GPU in a Jetson family member is of a particular generation, like Kepler, Maxwell, Pascal, just like we see on the discrete GPU side. And Jetson is different fundamentally because the physical memory that the GPU talks to is the exact same as the physical memory that the CPU talks to. They're the same DRAM device, and they ultimately go through the same memory controller. as a result of that, I can take advantage of things in Jetson that would not work or behave the same way in a discrete system. In particular, whether I use pin memory, which has been referred to earlier, and which I'm not describing in detail right now, or if I use managed memory, those are both methods to allow the same pointer to be used in host code or device code. Now, with respect to managed memory, we'll define pin memory in our next session. But with respect to managed memory, what we now know, at least in the modern regime, is that that carries with it an idea of demand paging. The processor that needs it touches the allocation, and if it's not physically resident, it causes migration of data to the processor that needs it. Well, in a Jetson system, if I do a CUDA-malloc managed allocation, there's no migration of the data. The pointer just becomes visible and usable, whether I'm on host code or device code, with no overhead associated with demand paging. If I didn't do that in a Jetson, if instead I used my ordinary CUDA-malloc methodology that we've learned about at the beginning of this CUDA training series, then I would have parallel allocations. I'd have an allocation using malloc, which would be in host code, and the pointer would only be visible or usable in host code. And I'd have another allocation which would be done to make that data available to device code. That would be done with CUDA-malloc, and that would be in a different place in the DRAM memory. But those two allocations would be holding essentially the same data in the same DRAM memory. And so that's not a very efficient use of memory on Jetson, and we can get around that and pick up a lot of other benefits as well by using managed allocations on Jetson. And one of the benefits we get is that there's only one allocation, and that same pointer is used in host and device code, and there is no migration of data because it's always available to the processor that needs it, whether that's the CPU or the GPU. Okay, that's enough discussion about Jetson. The question asks, even though it uses Maxwell, hopefully I have given some idea of why it is different. Even on Maxwell, if it's physically unified memory, which we don't have with the discrete GPU setup, if it's physically unified memory, I don't have to have migration of data. And Jetson doesn't necessarily imply Maxwell either. There are Jetson family members that use even Kepler. That's now obsolete. They use Maxwell, Pascal, Volta, and probably there will be other variants in the future. Okay, let's go back to some use cases now. So we're transitioning from an understanding of the underlying mechanism to how can we use this? What are some interesting ways that we can use this? And one of the first ways that we're going to look at is the idea of a deep copy. And so you might ask, well, what is a deep copy? A deep copy will occur in CUDA programming. It really is true in host code if I was making a copy as well, but let's ignore that for the moment. In GPU land, in CUDA land, a deep copy will occur anytime I have a set of data structures that I've depicted in the upper left-hand corner of this slide, and I then need to move that data to the GPU. So let's unpack that. We have two entities here. The first entity is in the upper left-hand corner. It's a struct definition. And let's imagine that I have an array of those structs that I have allocated for. Each struct member of that array, each object in that array, has a pointer in it called name. And presumably that's a char pointer, so presumably it points somewhere to an array of characters. And so in addition to just allocating in host code for this array of structs, for each object in that struct, I need to provide an allocation for the name pointer so it points to something real. Okay? And so I've depicted the arrow pointing to another entity. We're calling it a buffer, and that buffer has some allocated size associated with it, let's say len. Okay? And so these two items together are necessary for each one of these objects in the array of structs to be usable and coherent. And all of this might be something that I have already allocated in host code. Now the question arises, I'd now like to be able to use that array in device code. What do I have to do? I'd like to be able to use those structs, that array of data LM, and I'd also like to be able to access the buffers that each name pointer points to. And it's all existing on the host, and now I need to get it and use it and make it usable on the device. What do I have to do? Well, it's not a trivial set of CUDA mem copies anymore. The fact that we have an embedded pointer pointing somewhere else substantially complicates the code and makes our work more difficult and our life more difficult as a CUDA programmer in order to move this data structure to the device. Okay? And what I've depicted now is the sequence of operations that are needed in ordinary CUDA programming, not using managed memory, to make this work. In other words, to move this array of structs from the host to the device. Okay? And so I'm imagining that I'm going to create a function call to do that. That function call is going to be called launch, and ultimately it's going to launch my kernel. But the first thing it's going to do is take a pointer to an array of data LM, and I need to make sure that everything in that array, including its dangling pointers, including its name pointers, make all of that usable in device code. So the first thing that I'll have to do is create a device pointer to point to my array of structs on the device, and I'm calling that D_LM. And I have to allocate that device pointer of a size equal to the number of structs in my host array. Then I'm going to copy that entire array of structs in one blast to the device. And so far, things don't look to be out of whack yet, right? Because any step one in my CUDA processing sequence is going to have a CUDA malloc and a CUDA mem copy. So far, things haven't gotten off the tracks yet. But all this has done is move the array of structs, and those structs have embedded pointers in them, and those pointers are still pointing to something in host memory space. They're a host pointer. I copied it to the device, but that CUDA mem copy operation, that first CUDA mem copy, didn't fix those pointers at all, and it didn't do anything about the buffers. So I still have to handle those items. In order to handle those items, I'm going to use code like what I've depicted in this for loop. I'm going to have to go through every element in that structure. I'm going to have to create a buffer allocation on the device. And so for every element in the data LM array, I'm going to create a buffer allocation on the device. That's what char star dname and the CUDA malloc inside the for loop are doing. Okay. Then I'm going to copy the host buffer, the data in the host buffer, to the data in the device buffer that I just allocated. And then I have to fix up the pointer. I now have to make the pointer that's embedded in my data structure point to device buffer allocation instead of host buffer allocation. Okay? And I have to do that entire loop for all of my processing, in other words, for the length of my array, and then I can finally launch the kernel, and the data will be properly moved and migrated, and all of my pointers will be fixed up. This whole sequence of operations is called a deep copy, okay? And everything I've depicted here has nothing to do with managed memory. This is the way that you would do it if you were just writing ordinary CUDA code up until what we've learned, not including today. When we're using CUDA malloc manage, I don't even have a slide for it because it's dirt simple. When you were allocating in your host code and you allocated your array of data LM using malloc, you just changed that to CUDA malloc managed. When you were allocating your buffers in host code, you just changed that to CUDA malloc managed, and you're done. Everything else just works. When you when you call the kernel on the device, you don't need any of the stuff that I've depicted on this slide. All you have to do is launch the kernel with the pointer pointing to your data LM on the host, not on the host, it's in managed memory, and everything just works. So it's dirt simple. If I were to depict what it is, it would be just one line of code. Every other line of code on this slide disappears with managed memory. Okay. So let's extend that and think about a linked list. Now, I don't think I'm going to have time. I'm not going to go through an actual coding example of this. But another type of data structure, similar to what I had to deal with previously with the deep copy, that might use a similar methodology is a linked list. I might have an array of objects, and each object has a pointer to the start location of the next object. Okay? This would be what we're depicting here would be a singly linked list, and you might also have a doubly linked list. Taking a linked list like this and converting it, in other words, moving it from host to device using ordinary techniques is painful as a CUDA programmer. I would not want to have to write that code, okay? This is a deep copy and a deep copy and a deep copy in a loop. Okay? It's painful. It's trivial with unified memory. I just replace all of my host allocators. Let's say I was using malloc with with managed allocators, and everything just works. I can pass the pointer to the first object, to my device code, my kernel, and code in that kernel can then navigate object to object by following the pointers. Everything will just work. Here's one that requires a little bit more unpacking. It'll be, I think, the third out of 4 use cases that we'll talk about. So this one is taking our managed allocator and applying it to an overload of the new operator. As we know in C++, the new operator is a system allocator, and it can be used in a variety of different ways. And one of the ways it can be used is to allocate an object, and in fact to call the object constructor. Okay, and so if I use new that way to allocate an object, then it's allocating space for the object. It's also calling the object constructor. In object-oriented programming, I can also use inheritance to have other objects behave similar to a base object. And so what I'm going to depict here in this slide and the next one is a sequence of coding that will allow me to use objects that appear to be operating as if they were host objects, but equivalently and easily usable on the device. So what does that mean? Our objective will be to build a string class that will be usable in other objects. So the first thing that we're going to do is create a base class called managed, and that base class is going to do nothing other than override the new and delete operators, as I've depicted here on the left-hand slide, and the left-hand side of the slide, and we're going to overload those in a way that uses a managed allocator instead of what would normally be a system allocator, a host code allocator that's provided by the default implementation of new. Okay, so we're overloading the new operator, and we're now causing new to create a managed allocation instead of an ordinary allocation. And likewise, the delete operator is going to do CUDA free on this managed pointer. Okay, that's our base class, and if we inherit from that class, we will pick up that behavior for any use of new on the inherited class. Not in the inherited class, but on the inherited class. Okay, so the first thing that we're going to do is create a class called umString, Unified Memory String Class. It's going to inherit from managed, and it's going to assume that what we want to do is manage a string, and the string will have a length and a pointer to the data. Okay, and once again, we see an object with an embedded pointer, and so if we were handling this in ordinary CUDA code, immediately our worry flag would go up and go, oh no, I'm going to have to do a deep copy. Okay, anytime you see an object with an embedded pointer, that triggers the deep copy alarm when you want to move that object from host to the device. But this methodology will eliminate that alarm. So our object intends to manage a string of data, and the string has a length associated with it. The one thing that we need to do to continue to extend this object to make it workable is to provide a copy constructor. The copy constructor will allow one object of the class to be created from another object of the class. And this is actually necessary if we pass the class by value, for example, to a function. So our copy constructor is defined like this, and it's also using CUDA malloc managed, and then it's doing just a straight memcopy. So it's copying the length parameter, the length argument, and then it's creating a managed allocation for the data pointer, and it's copying the string data, the character data, from the other object to the self object using memcopy. Okay? So that's our copy constructor, and that allows the string class not only to have managed allocation if you create a new umString, but it also allows the string class to have a managed copy constructor. Okay, now we're going to create another class called DataLM, which will have a string class embedded within it. And so now I have my class called DataLM. It is also inheriting from managed, and it has embedded in it an object of type umString. Once I have created that class that way, I can create an array on the right-hand side of those objects using new. As I've depicted on the right-hand side, this looks like ordinary host code now. This is indistinguishable from ordinary host code if you don't go poking around into the definition of what a data LM class is, okay? But this looks like ordinary host code. I've created an array of those objects with embedded string objects, and this array is now directly usable in device code with no additional footwork or steps by the CUDA programmer. So that's a really cool capability of using C++ operator overload with new and delete to extend our managed capability into the object-oriented space. The last use case that I'll talk about is a very brief one. This is going to hinge on the idea of oversubscription. So we could imagine that I have a very large data structure that basically won't fit in GPU device memory. And furthermore, you know, with some algorithms, like if I'm just going through a large data structure in a structured way, like sequentially, for example, then as a CUDA programmer, it's not too difficult to arrange a sequence of operations that will allow me to work on that entire array sequentially in a very efficient fashion. And in fact, that's one of the topics that we'll be talking about in our next session in concurrency. We'll talk about how to handle that case in a very efficient fashion, chunking up your data and moving chunks of data to the GPU and letting the GPU operate on those chunks. And if I have a known access pattern, a structured access pattern like sequential, for example, then it's fairly easy to write the code to make that work. We'll see an example of that next time. But what if I don't know the access pattern? I know where I'm going to start in the code. I'm going to start in the code at the starting point, at the first point in my allocation, let's say. But thereafter, the process of moving through the code is data dependent. Now, you might be able to come up with a sequence of processing on CPU code that allows you to structure that, but it's going to be substantially more difficult. And it might be nearly impossible to do if the data-dependent nature of the traversal through the data depends not just on the data, but also on the calculations on that data. Then you really have to make those decisions at the point where you're calculating on the data, and presumably you're trying to do that in GPU code, in device code. So there is no way in that example, or in that case, that the CPU code can know a priori or even on the fly what the access pattern will be, and therefore how to intelligently move data to the GPU. And we can't just move all the data because it's too big. So demand paging and perhaps oversubscription neatly solves this problem, okay? I say neatly solves it from the standpoint of the programmer, not necessarily from the standpoint of performance, but it solves the complexity associated with the programming task by allowing the programmer to simply say, I'm just going to oversubscribe GPU memory so that I can have my entire graph present in the managed allocation. And then I'm going to launch my kernel. And as the kernel is going through from node to node in the graph, making calculations, and then based on those calculations, deciding where to go next, and then when it goes to the next node and touches the data associated with that next node, demand paging kicks in and brings that node to GPU memory. Again, there's almost certainly going to be some overhead or cost associated with that. And I will go back to the statement I made before. The GPU is a latency hiding machine. That cost is largely evident in the form of latency. And so if you can give the GPU enough work to do, enough exposed parallelism, and there's a reasonable amount of computational complexity with your code, then you might be able to hide the latency associated with demand paging. Okay. We're going to transition now to our last major topic, which will be on performance tuning. I'm kind of running over here, so I'm going to need to move more quickly. So one of the things I mentioned at the beginning of the presentation was that unified memory is not necessarily about performance. It's really the objective of it is really more towards programmer productivity and simplifying coding. Hopefully we got some ideas of how that may be. What new users to unified memory, especially if they make some naive choices, may often observe is that not only is unified memory not making my code faster, but in fact it's making it slower. In fact, it's making it a lot slower. Okay? And usually when they have that observation, when they put their toe in the water with unified memory, it's usually because demand paging is biting them. How and why is that happening? In the naive coding case, we would simply create our managed allocation and call a kernel, like the kernel that I've depicted here on the right-hand side, and the host code that I've depicted on the right-hand side. I create my allocation, and then I launch a kernel, and I just start working with that allocation. Well, what's going to happen is as the kernel code touches that allocation, page by page, it's going to create faults. And each fault causes the kernel code to be stopped and the operating system, both the CUDA runtime and the host OS, to intervene and do something, namely to move data. That process has some overhead, and if you do it on a page-by-page basis, sort of piecemeal, overhead is substantially higher than what you would get if you move the data en masse. And so this is why your performance can take a substantial step backwards. Not only am I not moving the data en masse, but the page-by-page movement has overhead associated with each page fault, and that can be problematic, okay? And so we want to allow programmers to use managed methods, but not necessarily be forced to put up with this sort of penalty, okay? And so for bulk movement, or anytime I know that I'm going to access a large chunk of memory, a memcopy operation, a CUDA memcopy-like operation is going to be much more efficient than relying on page faults to affect the movement of data. The page faults will work, but they have an associated cost. Okay, so the first thing that we're going to introduce is something called CUDA mem prefetch async. There's a lot of complexity to this, and we won't touch on all of the complexity, but in a nutshell, you can sort of think of this as being analogous to CUDA memcopy or CUDA memcopy async. You're giving it a pointer and a length associated with that pointer in bytes, and a destination device. What processor do I want to move this allocation to? Do I want to move this data to? Okay, and so from the programmer's perspective, so far as we've talked about right now, that is in some ways pretty similar to CUDA memcopy async. CUDA mem prefetch async ostensibly moves the data en masse and moves it all at once. Now, it's an asynchronous operation, so it may or may not begin to execute right away. And there is some complexity which you can read about if you wish to, using one of the links that I provide at the end of this session, okay? So it's not quite as simple as I've described, but for a mental model for where we want to start, that's a good place to start, is that it's a lot like issuing a CUDA memcopy async, okay? The difference here is that I can target a specific processor, and in some cases, the processor that I wish to target may be the CPU, okay? So how does that work? Well, on the right-hand side, I've depicted the same example as I had on the previous slide. And now what I've done is introduce two new calls, CUDA mem prefetch async before the kernel and CUDA mem prefetch async after the kernel. Okay? The one before the kernel is moving the data to device 0. That would be GPU, the first enumerated GPU in my system. And the CUDA mem prefetch async call after the kernel is moving that same data, the same size, the same allocation, back to the host. And it's doing it by, instead of passing a number like 0, 1, 2, 3, which would correspond to GPUs, 0, 1, 2, 3 in my system, I'm passing a specific token called CUDA CPU device ID. And this informs the CUDA mem prefetch async call that wherever this data is on whichever processor it's on, I want to make it physically resident in CPU memory, okay? And if I do these two operations this way, this will essentially restore performance. At this point, my kernel will appear to run at the same speed as it would run if I was using an allocation provided by CUDA malloc, okay? All right. So that's a basic technique that you should be aware of using CUDA malloc managed. We have some additional what I'm going to refer to as sort of finer grain performance tuning techniques. And most of these depend on the idea that a managed allocation is an allocation that has a processor association. It's not an explicit one, but it has a processor association based on the processor that needs it, the processor that's trying to use it, the processor whose code is touching that data. The managed allocation or pages of that allocation will move to that processor. That's what unified memory does, okay? Now, if I just allow this to happen with no additional input or smarts, I can get into some situations where the overhead of my data migration can be problematic for my code. And so we're going to introduce something called some hints, and the hint mechanism uses an API call called CUDA memAdvise. And these hints allow us to inform the unified memory runtime, or the CUDA runtime, that operating system that's handling steps 1 and 3 for you, that's handling the migration of data. We're going to inform that operating system about some things that we know or would like to see about the usage of the data or its processor locality. Okay? And presumably we're going to do this based on our knowledge of the code that we have written. The unified memory system doesn't grok or understand all of the code that you've written. It's not anywhere near that smart, and instead it's trying to make decisions on the fly. So we can aid it by giving it some hints, and this is how we provide hints. There's 3 hints that we'll talk about. The first one is called CUDA memAdvise set read mostly. What this specifies, I'll depict each of these 3 on 3 slides, but this basically says that this data is primarily going to be read by most processors, and it's going to create duplication of the data. We'll see what that means in a minute. Another hint that I can say is for a particular allocation, I can say CUDA memAdvise set preferred location. This simply suggests, it's a hint to the runtime that probably it would be best if this data were resident on this processor. And then you can further add some hints by saying CUDA memAdvise set access by, and this will suggest to the runtime that some other processors are going to need to access this data, and I would prefer not to create migration in that case. Instead, I would like to create a mapping, and I'll explain what that means. So we're going to go through each of these 3 hints, and let's keep in mind that they're hints. They're basically suggestions to the runtime. They don't guarantee most things, and they don't trigger data movement by themselves. None of these hints are like CUDA mem prefetch async. They don't force migration. We'll see what that means. So CUDA memAdvise set read mostly says to the runtime, the unified memory system, that the data will mostly be read-only, basically by all processors. And that means that the unified memory system will make a local copy of the data for each processor that touches it. Now, when I have multiple copies of the data, immediately the question arises, well, how do we maintain coherence? If a processor writes it, and I have 2 copies, how does the other processor see that update? Well, the idea behind CUDA memAdvise set read mostly is you're telling the UM system, hey, I'm not going to do that. Now, this isn't a contract. What you're telling it is, hey, I'm not going to do that, and it's going to take you at your word and create copies. And as long as every processor only reads its copy, everything's fine. As soon as one processor writes, in other words, violates your hint, then the unified memory subsystem will go in and invalidate all that and force migration again in order to make the data coherent. Okay? So it's not a contract. There's nothing for you to break. You can set this hint and still do whatever you want, and it should work. Okay? But the benefit comes from when you actually adhere to your hint and your processors are only reading their data. Every processor gets its own local copy, and there's never any migration. Okay? I don't want to say never. What I mean is there will be migration on first touch. There always is. Okay? So when a processor first touches an allocation, a managed allocation, there's always migration. Okay? Except if that allocation has never been touched by any processor in the system. But presumably that's not the case for read-only data. So if a processor touches read-only data for the first time, there's going to be migration at that point. But subsequently, that data will never disappear. Even if other processors are reading it, it's not migrated to those processors, and therefore every processor after first touch appears to have full speed access. Okay, let's go to our next hint. This is telling the memory system which processor do you think is the best location for the data. Again, it's not a contract. Unified memory should still work correctly and give you the correct answer even if you violate your hint. But what you're saying is that I believe, let's say that I have 2 GPUs, and the first GPU is where I want this data to be located. So I hint to the unified memory system that I would like to set preferred location to that first GPU. And again, none of these hints create any migration, so that does nothing initially except inform the UM system. When the first GPU touches that data, migration occurs. okay, and it becomes resident on that GPU, just like you hinted, okay? Now, when the second GPU touches it, what the system will try to do is create a mapping, and this means that when the second GPU touches that data, instead of migrating the data to the second GPU, it will create a mapping, and it will service read and write requests over the interprocessor bus. So if that bus is NVLink, like it is on Summit, it will service it over NVLink. If it's not NVLink, it will service it over PCIe. This also requires some, in order for this to work this way, it also requires those GPUs to be in the same PCIe click, or basically accessible by the same PCIe root complex. Okay, so there's some complexity there, but you shouldn't have to worry about that on a system like Summit. Okay, all right. If the mapping is not possible, then the data will be migrated. Okay, so again, none of this stuff should cause anything to break. You're providing hints to the system. If those hints turn out to be a correct analysis or the behavioral description of your code, you're likely to benefit from a performance standpoint. If the hints turn out to be not correct, it shouldn't fall over. It should still work. You should still get the correct answer, but it may run slower. Okay? In addition, even if you don't do any hinting like this, Volta processors and beyond add something new to the unified memory hardware. In particular, they add something called access counters. Those are looking at the various interprocessor links, PCI Express and NVLink. And I think actually it might be just NVLink. But in any rate, they're looking at the interprocessor bus, and they're using those access counters to figure out who is using this mostly, or what is the organization of data access, what does the preponderance of data access pattern look like, and then it will try to make some intelligent decisions for you for migration and or mapping of the data based on those counters. That's all a mechanism under the hood. It's not really directly exposed to the programmer. It's like a cache. If it gives you any benefit, it just happens for free. Okay? And the access counters are mostly orthogonal from a CUDA programming model standpoint, are mostly orthogonal to the hinting mechanism. Okay? So the hinting mechanism doesn't necessarily depend on the access counters, but it may benefit from the access counters. The last hint that we'll talk about is CUDA memAdvise set access by. What this says is, for a particular processor that you're pointing to, it says that if possible, have this processor access the data using a mapping instead of migration. Okay? So it provides access without incurring page faults. That's the benefit of a mapping. It's still slower than ordinary access, but a mapping allows you to access it over the bus and doesn't require a page fault to service the access. Okay? And so if you know that a processor will occasionally access data that you know is resident on another processor, then you might want to give this additional hint of set access by. That causes the runtime, in other words, the unified memory system, to create a mapping for you. And then when the processor accesses it, it will access it using the mapping over the bus instead of triggering a page fault and migration. Okay, we're almost done. I just have a couple more slides on some various and sundry topics. For this slide, I just want to remind everyone that unified memory is first and foremost about programming, the programming model and ease of programming and productivity, not about performance. A well-written, optimized CUDA code that's written by an expert using CUDA malloc and ordinary 1, 2, 3 processing sequence will not be worse than a unified memory realization, okay? Because you as a programmer know better than the unified memory system. So you could sort of think of that case as being the upper bound for what unified memory can achieve. Unified memory and concurrency also have some interesting interactions, and one of the links that I give at the end of this session for further study will go into that in a little bit more detail. I may mention this in our next session on concurrency. I think I might, so we may revisit that topic in a limited way. We've already seen, or at least hopefully understood anyway, that misuse of unified memory can slow a code down dramatically. It shouldn't break it, shouldn't give you the wrong answer, but it can certainly impact performance. And there may be some particular coding scenarios, perhaps that graph example that I gave you might be one, There might be some scenarios where unified memory might enable a particular design pattern that's otherwise quite difficult to do with an ordinary CUDA 1, 2, 3 programming model. Oversubscription is also something to be used with care. It does not easily or magically give you access to larger memory. There's a cost associated with it. If you can hide that cost using the latency hiding capability of the GPU, great. If not, you may observe disappointing performance with oversubscription. It'll still work, but it may just run slow. And unified memory also may be a simplification method to allow you to integrate many different libraries which are not really paying attention to each other, or may be written independently, and allow you to have all those libraries work together in sort of a consistent and coherent fashion. Okay? So one of the final points I'll make about unified memory is it's also used as a rapid porting model. In other words, if you want to do a quick port of a code, you can literally just go through the code and change all of your host memory allocations to managed memory allocations, and just like that, you've handled step 1 and step 3 of the CUDA processing sequence. Everything's done for you. Not necessarily in the most highest performance way, but everything's done. Now the only remaining step is to actually port the pieces of code where you're going to do processing on the GPU into CUDA kernels. So it can be used for rapid code development or rapid porting. Okay. We're not going to say much about multi-GPU. Multi-GPU is a topic we'll talk about in the next session briefly, but Pascal plus demand paging just works in a multi-GPU scenario. Like I said, the idea behind managed memory is to migrate the data to the processor that's asking it. In a multi-GPU scenario, it can be any processor, any of your GPUs, and it just works. You can also use prefetching and or the hints that we talked about to guide the system migration behavior. Power 9, the processor that is in Summit, for example, has some particular characteristics that pertain to the memory system that we will talk about now very briefly. We know or have a good idea of what unified memory is now, and we mentioned that unified memory, or UM, is also called managed memory. Those are synonyms. The next thing that we want to talk about is something called ATS. So ATS is Address Translation Services, and it's today anyway, I would describe it as a unique characteristic of the marriage between CUDA GPUs and IBM Power 9 processors. And in a nutshell, what it does is allows for CPU dynamic memory allocations like malloc to be accessed in GPU code, any GPU. This is kind of a shocking and striking statement to make, because it totally throws out the window some of the things that we've learned from day one in CUDA. Okay? So if I'm on a Power 9 system like Summit, and I do a host allocation using malloc, that malloc will return a pointer. That pointer can be used directly in device code, and you should expect to get the correct results. Okay? That's a remarkable statement. Okay? It's unique to this scenario, and it's facilitated by a hardware mechanism that includes, amongst other things, a feature called ATS, Address Translation Services. The data is not migrated, so it's not exactly the same as unified memory. Okay? The data is not migrated, which means when I access that pointer that was returned by malloc in host code, or ordinary new in host code would be another example. When I access that pointer in device code, the data is not migrated, and so instead there are bus transactions occurring across the CPU to processor bus, or CPU to GPU bus. Okay? In a Power 9 system, that CPU to GPU bus is NVLink. Okay? So these transactions, these read and write transactions in device code on the GPU will cause bus transactions to occur across the NVLink connecting that GPU to its CPU, and will then access the CPU memory directly that way. So we can expect that that's going to be lower performance in many scenarios. Okay? I don't have enough time to go through all the performance implications of this, but it will be lower performance. Finally, as I mentioned, this idea of using an ordinary host pointer in device code is a shocking and striking statement that should immediately raise the eyebrows of any CUDA programmer. Okay? That's an unusual thing. Doesn't work in ordinary CUDA plus x86 systems. Does not work, and if you tried to do that, your GPU code will hit a fault and it won't give you the right answer. But NVIDIA and others are also working on a slightly different mechanism to make a similar capability possible in future architectures, future CPU, GPU architectures, and it will probably depend on an implementation of something called HMM, hybrid memory model, in the Linux kernel. That's just a forward-looking statement. I don't have schedules or statements about functionality or behavior at this point. I just want to let you know that that is something that's in the works. So with that, I believe I'm at the end of my presentation. I apologize, I've kind of run longer than I expected to here. So we have a few sessions left. July, August, and September, I think, is the way those map out. I have some recommendations for further study, and there's homework. So what I'd like to do now, we're going to probably end up using most of the 2 hours, but what I'd like to do now is try and pick up with the chat, then we'll throw the mic open, and lastly, we'll turn it over to Robbie if we have any time left. Okay. Looks like there's just maybe two additional questions in the chat. Is there any cost with using managed memory if all the memory can fit on the GPU by itself? Yes, I would expect there would still be a cost, but it depends on how you use it. If you just did an ordinary allocation using CUDA malloc manage and then launch a kernel and that entire allocation can fit in CUDA device memory, I'm still going to trigger those overheads associated with demand paging. We've kind of talked about that already. If, on the other hand, I use CUDA mem prefetch async prior to the kernel launch, I would expect that that case behaves identically. In other words, there's no cost. That should behave almost exactly the same way as if you used CUDA malloc for that allocation and did a CUDA mem copy operation. Is it necessary to do device-wide synchronization, or can one do it at the CUDA stream level? It is necessary to do device-wide synchronization. I assume that is referring to the statement about using CUDA device synchronize after the kernel in the pre-Pascal regime. That has to be a CUDA device synchronize call. CUDA stream sync doesn't get you there. However, if we talk about the post-Pascal regime, the modern regime, the one that exists on Summit, there's no synchronization at all needed unless you need it for some reason. And if you need it for some reason, you can implement it however you like. A stream sync should work in that case. Last question. For the 2-node Summit run, I CUDA malloc an array, then use NVLink to send the array to another GPU in a remote node. I don't think so. Unless you're talking about...
Bob, I can take this one if you don't mind.
Okay, go ahead, Max. Take it away.
So what this question is referring to is the concept that you can use buffers in MPI for an MPI job on a system like Summit, and you can pass buffers that are device pointers. And so the MPI implementation on the system knows how to handle that. And so when you send data from one node to another node with this so-called CUDA-aware MPI, which is, I believe, what's being referred to here, then indeed what Bob is saying is right. That doesn't actually use NVLink the whole way through. There is no NVLink connection between the 2 nodes on the system. There are InfiniBand adapters that connect the 2 nodes in the system. And so what many CUDA-aware MPI implementations end up doing is that for transfers that occur between 2 nodes, one way that they can do them is they can copy data from the device to a temporary buffer that lives on the CPU, and that buffer is typically pinned to memory for performance. So that's why you'll see that occur in Insight systems. And then similarly on the remote node that you're sending to, it'll copy to the pinned buffer on that remote node and then copy back down to the other remote GPU. It is possible for that transfer to occur in a different way. It's possible for the GPU to go through NVLink, well, really through PCIe actually, to the InfiniBand adapter directly without going through the CPU, and then traveling over the network to the other server node, and then copying to the remote GPU. And then that's another way to do it. But either way, there's not a connection all the way through NVLink from one GPU to another GPU if you're going between nodes. If you were copying from a GPU on one node to a GPU on the same node, then you can do that with a peer-to-peer transfer, and the MPI implementation knows to do that with a peer-to-peer access in that case. So the difference is really that there is no NVLink connection between the other nodes, multiple nodes in the system, and that's why you have to take a different path for the one node and two node cases. Hopefully that answers the question.
Thanks, Max.
Perhaps I should also answer the question that we did not answer earlier on. So somebody asked the question, okay, the question specifically was, are the CPU pages allocated with CUDA malloc managed mapped by the OS page fault handler or something in the CUDA runtime and or NVIDIA UVM driver? So the exact answer to this question is complicated, and I won't give it. But let me answer it with a kind of high-level view that I think is useful. So for both NVIDIA Unified Memory, the way that Bob described it today, as well as ATS and the future HMM support, you can think of all of these things as kind of an interposing layer where we don't change the fact that both the CPU and GPU, to kind of first order, have a memory management unit which includes a page table that maps virtual addresses to physical addresses and includes things like a TLB that caches those accesses. And all of these technologies are essentially an interposing layer where before a page fault would occur and then would be handed off to the CPU or GPU normal page fault handler, we check essentially this table. Is the page available on the other processor on the system? The actual details of how that works are different between the technologies. So with ATS, that's really occurring as a hardware translation. Whereas with the NVIDIA UVM implementation or this proposed HMM implementation in the Linux kernel, these are software translations that occur. Nevertheless, the underlying implementation hasn't changed from the fact that you have a CPU or GPU page faulting, but it's kind of an interposing layer that says, before we do this page fault, check to see is the data that we need occurring on the other processor that we want to access, and then if so, grab it from the processor rather than triggering an initial page creation.
Thanks, Max. Excellent. Appreciate it. What I'd like to do now is throw the mic open for any spoken questions, and after that, I will transition it over to Robbie with whatever time is left. We may not get through all the homework. I apologize for that. If anyone would like to ask a spoken question, please do so now.
Hey, Bob, this is Tom. I had a question about the oversubscribing GPU memory. So you had mentioned that if you were to exceed, say, 16 gigabytes of memory on the GPU, that you would start evicting pages.
Yep.
When you say that, if, for instance, the very first thing you do in a code is, CUDA malloc manage some memory that's larger than GPU memory, and you start filling that array or something on the GPU, and once you exceed the first 16 gigabytes of memory, you start moving on, right, and evicting pages. Is that, when you say evict pages, are those pages being transferred to the CPU to hold that information that you've already stored in those in memory?
Yes, they're being transferred somewhere. They're being transferred somewhere, because if we didn't transfer anywhere and we evicted it, we would lose the contents of those pages. So yes, they're being migrated. The CUDA programming model, as far as I know, does not specify the direction of that migration, but it's migrated to some other processor. And I would generally make an assumption, without knowing that this is conclusively defined, that that processor that it migrates to would typically be the CPU.
Okay, so even if the CPU, the actual memory
had no reason to touch or need that page, it might still migrate back to the CPU.
Okay.
Because we need a physical copy of it somewhere before we can actually evict it or unmap it. Unmapping isn't the right word. Before we evict it from physical mapping in the GPU memory.
Okay, that makes sense. Just wanted to.
We need to have made a copy of it somewhere.
Okay, thanks.
If there's not any other questions, then I'd like to, for the last 15 minutes or so, I'd like to make that available to Robbie. Is that okay? Robbie, do you mind jumping in at this point?
No, that sounds good.
Okay, I'm going to stop sharing.
All right. While Robbie is taking over, I just wanted to take the opportunity while folks are still here and Bob is still on the call. I just wanted to thank NVIDIA for presenting these modules of this training series. We really appreciate you guys doing this and look forward to the next ones. Speaking of next ones, there, as Bob pointed out, and I dropped links in the chat too, there are upcoming modules as well. And we also have a survey. If you could help us fill that out, it does help us improve these events for the future. So thanks to NVIDIA, and also thanks to NERSC for their side of the organization as well.
Yeah, I would also like to thank NVIDIA for Bob's extensive deep knowledge presentation, and for Tom for organization, and Max and Robbie for going through and answer questions, demo, etc. So Cori users, you're added onto the GPU node again, and you have 1 week to access until next Thursday.
All right.
I'm sorry.
So,
Okay, sorry, go ahead. Nope, sorry, go ahead.
I was just going to get started on the homework.
Yes,
if you have anything to add.
Nope.
All right. Okay, so if everyone goes to the, first of all, can everyone see my terminal window?
Yep, I can see it.
All right, cool. So for anyone on Summit, if you look at the homework 6 directions, the first there's 2 steps. First, we're going to port a linked list application using unified memory, and then we're going to do a profiling exercise to show you how your code is going to behave. First thing we're going to do is load CUDA. I have an interactive session already. I kind of prepared that to hopefully speed this up a little bit. I'm also going to, for the sake of following my own directions, I will create an alias here. Okay, so the first thing we're going to do is we're going to take this linked list application and we're going to convert it to use managed memory. So this is a really, really simple application. If we look on my screen here, we have this allocation function. So this is going to be the first thing that we're going to change. Basically, anytime in your code, as we mentioned in the lecture, anytime in your code that you have any kind of memory allocation, you're going to change that to use CUDA malloc managed. Which will look something like this. And notice that we actually already have a CUDA device synchronized following our kernel launch. So that's good. For this particular example, this is kind of the easy part of the homework assignment. That should be the only thing we have to do here, except for no, I think that's the only thing we have to do. We should be able to compile and run this and get the correct answer. Let's see. Unless I missed something. Oh, okay. Looks like everything is working correctly. The correct output is in fact that. So that's kind of the easy part, just to kind of give you a quick overview of how simple this can be. But now what we're going to do is we're going to go into this array increment exercise, and we're going to do a couple things. First, we're going to compile and profile the code as is, and it's already implemented by manually moving our data to and from the GPU. Then we're going to modify it to use managed memory, the same way we did for the first part of this exercise. and we're going to look at the difference in our runtimes and specifically we're going to look for how many memory operations are going on. Then we're going to use prefetching, which Bob mentioned in the lecture, to see if we can even out that runtime discrepancy between manually moving our data to and from the GPU and using managed memory. And then I have a bonus exercise where we can sort of do something that simulates a more realistic use case. So first, we're going to compile and profile our code as is. So first thing we need to do is load the profiler. So we're going to use Nsight Systems. Then I am going to compile the code as is. And then I'm going to run the code. Before I make any changes, I'm just going to run the code. I want to see what exactly our runtime looks like by doing a traditional implementation where we manually manage our data movement. And with Nsight Systems, I use the -- stats equals true flag to give us a printout, which you can see here on my screen. And there's a couple things I want to note on this printout. First of all, we have our kernel statistics here. So we have a total runtime in nanoseconds. And then we have a section related to our memory operations where we see a number for our copying from host to device and device to host. So we just kind of want to make a mental note of that. And then we're going to go back into the code and implement managed memory. So the main thing that I want to highlight here is we're taking something on the order of 400,000 nanoseconds. Before making any changes. Now we're going to do the same thing that we did to our linked list application, where we're going to use CUDA-malloc managed. And then down here, we're going to have to make a little bit of a change because first we had done a CUDA-malloc for some device memory. We don't need that anymore. We had used that device memory in our kernel launch. We do not need to do that anymore. We will switch back to referencing our host array. We don't need these CUDA-mem copy operations because we're using managed memory now. And I'm going to add a CUDA device synchronize here. I think that's all I need to do here. So let's recompile this. It's warning me that my device array was declared but never referenced. That's okay because we're no longer using it. And now I want to see what this runtime looks like. Okay, so now if we go back to our kernel statistics, we see a total time of 35 million nanoseconds versus 400,000 nanoseconds. So this has gotten significantly slower. And Bob mentioned that this sort of thing can happen where, you know, the upside of using managed memory is it's very easy to write your code. You don't have to worry about moving data to and from the GPU. The downside is that generally speaking, you're going to take some kind of performance hit. So notice in the assignment, it says now modify the code to use managed memory. We did that. Replace the malloc operations with CUDA-malloc managed and eliminate the CUDA-mem copy operations. Do you need to replace the CUDA-mem copy operation from the device to host with a CUDA device synchronize? Why? Now compile and profile the code again. So what that's saying is, do you need to replace the mem copy from the device to host with a CUDA device synchronize, which for a pre-Pascal implementation you would have to do. We've compiled and profiled the code again. We see that the kernel execution duration is significantly slower. And as Bob mentioned, we can use prefetching to overcome that. So prefetching is going to require us to go back into our code and modify it a little bit more. But it's not super difficult to do. Oh, didn't mean to do that. So basically, I'm going to do 2 prefetches in this code. I'm going to add a prefetch before my kernel launch. And here what I'm saying is I'm going to prefetch the host array and copy it over to device 0, so that's going to be GPU 0. And then as Bob showed on one of his slides, I'm going to do the same exact thing after my kernel launch, except I'm going to change that device ID to CUDA CPU device ID, which means I'm telling the managed memory system, hey, I want this memory to go back to CPU memory. And this should give us the result we want, where our performance should be somewhat similar now to if we were to just not use unified memory and manually move our data. So yeah, we can see now our kernel statistics, we're seeing a total runtime of 421,000 nanoseconds. That's very similar to our first run. It's also worth highlighting the number of operations here. So if I go back to before I put any prefetching in here, I'm seeing for copying my, actually, this is weird that this is showing me device to host first and then host to device second. But for host to device transfer, I'm seeing about 475 operations. And for device to host transfer, I'm seeing about 640 operations. And if I go back down here to where I'm using prefetching, I see 64 for both. So that kind of helps explain why there's such a big difference in runtime. We're not getting any page faults when we're using prefetching here. Now, the other thing I wanted to highlight here is if we look at our breakdown of our runtime, you'll notice that CUDA malloc managed is taking 96% of our runtime. So for this exercise, using prefetching is super important. And this example might be a little bit not so flattering for managed memory. But it's important to note that in this particular example, we're allocating a bunch of data and copying it over to the GPU. We're launching a very small kernel, and then we're copying all of that data back. Typically, in a real-world application, we would not do something like this. Typically, we would like to copy a bunch of data onto the GPU and operate on it many times, before we then transfer back to the host. The idea is to use the GPU for as much of your application as possible. So I put a little bonus exercise in here that says modify the code to run the increment kernel 10,000 times in a row instead of once. What can be said about the impact of memory operations on our runtime? What would this suggest for a real-world application? So obviously, again, this is a little bit of a silly example because you're probably not going to just run the exact same operation 10,000 times. But I wanted to highlight that right now we're seeing 96% of our runtime taken up by CUDA malloc managed, and we see exactly 0% of our runtime. It's a very, very negligible portion for this CUDA launch kernel. And since we're pretty much out of time, I don't think I have to go through the motions of that, but basically you can just write a for loop around the kernel to launch it many times. You'll get an error saying that the expected result was 1 and you're getting 10,000 because you're incrementing this array 10,000 times now. But what you'll see is your runtime will be dominated by your kernel launches instead of your CUDA malloc managed calls. And this is just to highlight that even though you will take some type of a performance hit using managed memory, it's not always the end of the world in your application. It does make it a lot easier development-wise. You can also think of it in some cases as a starting point where maybe you just want to replace all your malloc calls with CUDA malloc managed and then kind of focus on writing your compute kernels before you then start optimizing data movement. There's also cases where it might not be feasible to manage data yourself. So if you have some complex data structures, we used an example of a linked list in exercise 1, but it's conceivable that if you have many complex data structures, it might become a little bit overwhelming to do all that memory management on your own. There are solutions in here that are pretty much going to show you the same thing that I just showed you. Fortunately, this homework is relatively short, so because of how easy unified memory is to use. So does anyone have any questions about that?
Hey, Robbie, can you scroll back up
Yeah.
to the output from when you ran the sort of first iteration of your managed
Of my
managed memory, where you didn't do the prefetching yet?
Yeah, that would be this.
Sorry.
This is where we see a much longer runtime in this 35 million nanosecond, which I think would be like 0.03 seconds.
Sorry, and that is the kernel?
Yes, so there's two sections here. There's our kernel statistics, which is effectively our total kernel runtime, and then there's the memory operation statistics. So this just shows us how many host-to-device operations and how many device-to-host operations there were.
Okay. Yeah, sorry, I'm not familiar with looking at the nSite output still. I should
so the other thing you can do is, rather than using this stats flag, the reason I did this stats flag thing was because it's easier to show you guys my terminal than it would be to output this to a file and actually open it with the GUI version. But you can do that. You can just output it to a QGREP file and download it to your laptop and look at it with a, it'll give you a timeline then and be a little neater to look at. But
okay.
But you can use the stats equals true flag to sort of just dump all this information to your terminal.
Yeah, so I guess something that I would reiterate is that Robbie already said is in the first case that we're looking at the profile there for, where he doesn't do the CUDA prefetched, is that that long time that's happening there is because of all the page faults, right, Robbie? Is that the case?
Right.
This is happening because you're getting a bunch of page faults. So if you did what you, and again, I guess I'm just reiterating here, when I first saw an example like this, I would think, okay, well, I could have just done this with, I'm already doing a data transfer to and from the GPU. Now I'm doing this prefetch. I'm essentially doing the same thing here, right? And just, again, reiterating what you're saying is that if you had more work on the GPU, or you were calling more kernels or having something happen in a loop, that only that first kernel would be doing all of the page faulting. And so it sort of gets bloated in that way, whereas the next ones would run in a much shorter period of time. So just to point out.
Well, that's assuming that there's
exactly
no operations in between those kernel launches. Yes.
That's right. Yeah.
If you then try to touch that memory on the host in between your kernel launches, then it'll get messy.
And also your CUDA malloc managed up there, where you show the actual API call, that is bloated because it's the first call and sort of it eats that initialization, or it is actually just a longer.
No, it's because it's the first call. It doesn't. That's 0.4 seconds for that call.
Okay.
CUDA malloc manage doesn't normally take 0.4 seconds, but because it's the first CUDA API call in the sequence, it incurs some CUDA lazy initialization overhead.
That's right. Okay.
You can prove that to yourself pretty easily just by having a code that has more than one CUDA malloc manage call, and you'll see that the subsequent ones are much shorter than 0.4 seconds.
Okay. Okay, thank you. I was just sort of trying to clarify to myself while saying it out loud to other folks that might not have understood exactly what was happening with the elongated kernel time. Thank you.
Yeah, it's also compounded by the fact that the kernel itself, the actual kernel launch, is so short that it puts a percentage number that is pretty scary and big for this particular example, but that would not be representative of an actual code.
Yeah, I think then the bonus example that you said sort of makes it clear for everybody. But for the folks who maybe don't go on to do that example problem, I guess just I wanted to reiterate that. Thanks.
Sure. Does anyone else have any questions? All right, well, we're a little bit over time, so I'll try to breeze through that a little quickly. Like I said, this is one of the shorter homeworks, so that kind of works out for this particular module.
Okay, thanks everyone. I think that's the end of our session today. I want to once again thanks our hosts, Tom and Helen and the others at Oak Ridge and NERSC, and we will see you next month.
All right, thanks everyone. We appreciate you presenting these topics for us.
Thank you all.
No problem.
Processing the videos and upload it.
Yep, we should have the slides are up now on the event page, and the recording should be up in short order.
All right, well, we'll see you guys next time.
Thanks a lot, Robbie.